Assalamu alaikum. Welcome to your lecture today in Principles of Computer Networks. In this lecture, we will continue discussing medium access control sublayer. In this lecture, we will cover the Ethernet, wireless LANs, and data link layer switching. IEEE 8.0.2 has multiple standards, from which 802.3 for wired LANs and 802.11 for wireless LANs are the survivors, and 802.15 Bluetooth and 802.16 wireless LANs are potential, and the rest are now inactive. IEEE 802 architecture consists of physical layer, medium access layer, and logical link control sublayer. The physical layer has 802.3.4.5.6.11.12.16. Same applies for the medium access layer, 0.3, 0.4, 0.5, 0.6, 0.11, 0.12, and 0.16. As for 8.802.1, this is the standard for bridging, which we're going to discuss shortly in this lecture. And the 802.2 is for the logical link control, which we will also be discussing. 802.1 is for management, and 802.10 is for security. The logical link control works simply by receiving packets from the network layer and passing it to the medium access control sublayer after adding the logical link control header to it. The logical link control provides unreliable service, datagram service, and acknowledged datagram service, as well as reliable connection-oriented service. Logical link control hide the differences between various kinds of 802 networks from the network layer and provide a single format and interface to the network layer. As you can see here, the logical link control receives the packet, adds its header to it, passes it to the medium access control, which adds a header and a trailer and passes it to the physical medium. Now we're going to discuss IEEE 802.3, the Ethernet, which is the most famous LAN of all times. We will discuss the classic Ethernet and the switched Ethernet, fast Ethernet, gigabit Ethernet, and 10 gigabit Ethernet. The classic Ethernet has three types of wiring: 10-base-5, and that is thick coaxial cable with a controller in the network interface card and transceiver at the cable with the vampire tab. Then came the 10-base-2 Ethernet with thin coaxial cable, and the transceiver now is with the controller at the network interface card, and a connector at the cable. The last one is 10-base-T, which used twisted pairs, unshielded twisted pairs, and hubs. The thick Ethernet, which is now obsolete, consists of transceiver to transmit and to receive, transceiver cable, which consists of two pairs for data, two pairs for control, and one pair for power supply, and interface board, that's the controller, to frame, to calculate checksums, and to control the flow. The physical layer topologies, there were four physical layer topologies. The first was linear, where all the stations were directly connected to the cable, and that means if one station was down, the whole cable was down. Then the backbone topology, where stations are connected to a backbone, and that means when a station is down, only one station is down. Then came the tree topology. Last but not least, the segmented topology, segmented by hubs, by repeaters. Classic Internet physical layer is responsible for defining the bit in terms of duration and voltage. For 0 volt for 0 bit and 5 volts for 1 bit, it's difficult to tell the difference between idle sender 0 volt and 0 bit, which is also 0 volt. If the station sends, for example, a string of triple zeros, 1 triple zeros, others might falsely interpret it into 1 6 zeros or 0 1 5 zeros. If we chose -1 volt for 0 bit and 1 volt for 0 bit, the receiver might sample a signal that at slightly different frequency, which will make it out of synchronization. To resolve this ambiguity, we can use Manchester encoding or differential Manchester encoding. In differential Manchester encoding, which is used by the token ring, 0 presents transition and 1 is absence of transition. While in Manchester encoding used by the Ethernet, 0 is low-high and 1 is high-low, as you can see in the graph. The frame format differs from the old Ethernet, the DICS Ethernet, to the standard Ethernet, the IEEE 802.3. The difference, actually the only difference, is that the DICS has a type field while 802.3 has a length field. Both frames has preamble, 8 bytes with a bit pattern of 101010 used for synchronization. Both frames has destination address and source address with 2 or 8 or 6 bytes. It depends on whether it was unicast, broadcast, or multicast, and a type or a field length where the difference is. Then a data field with 1,500 bytes as maximum and 64 and 46 bytes for minimum, and a checksum of 32 bits that use CRC. Ethernet uses SYSMA with collision detection, and the question here is how long does it take to find out whether there was a collision or not. If A sends a frame to B and the time for the frame to reach B is tau, at tau minus eta, a collision happens. The noise from the collision will take tau to reach back to A. That means the collision detection can take as long as twice the time of transmission. That means all frames must take more than t, the round trip time, to be sent. If we send the frame too quick, we will miss the collision. If it took more than t, it will assure the success. For example, for 10 megabits per second LAN with maximum length of 2,500 meters, when 4 repeaters, t is about 50 microseconds. At 10 megabit per second, 1 bit takes 100 nanoseconds, 500 bits take 50 microseconds. The frame is 512 bits, the shortest frame. The MaxSupplier protocol is very simple. The time is divided into slots. The slot is 51.2 microseconds. After the first collision, each station waits for either 0 or 1 slot before retransmitting. After the second collision, each station picks either 0, 1, 2, or 3 at random and waits for number of slots of time before retransmission. After ith collision, the stations picks either 0, 1, 2, up to 2i-1 at random and waits for the number of slot times. At the 10th collision, the maximum slots is 1,023 slots. And after 16 consecutive collisions, the controller will report failure back to the computer and reset the connection. The classic Ethernet cabling Originally, it was thick coaxial cable that runs for 500 meters and has 100 nodes per segment. It was divided by repeaters, and this was the original cable, and it's now obsolete. 10 base T thin coaxial cable runs for 158 and 85 meters, and it holds 30 knots by segment and it doesn't need hub. 10 base T with twisted pairs run for 100 meter and holds up to 1024 knots, and it uses hubs. 10 base F fiber optics, it runs up to 2000 meters and holds 1024 knots per segment, and it's best between buildings. The efficiency of 10 base T with 512 bits slot time increases with the channel efficiency increase and decreases with the number of stations are there to send. It increases with the size of frame also. Usually, the classic Ethernet use hubs as a single point of concentration where all the lines enter the hub and are concentrated in a single point. Then if a frame comes from one line, the hub will transmit it to all other lines. The switched Ethernet, on the other hand, uses switches where the lines are enters a certain port, and the switch will send the data only for the port in which the destination is connected. When a station wants to transmit an Ethernet frame, its output a standard frame to the switch. The switch will actually, if it's destined for a station at the same port, it will be copied. If not, it will be sent over the high-speed backplane to the destination station card through the other port. If two machines attached to the same plug-in card transmit frames at the same time, there will be collision. But the switch has buffering mechanism so that the frame will not be lost. A switch can be used to create point-to-point links from stations or to be used as a concentration point linking a hub. Fast Ethernet has two high-speed Ethernet FDDI and fiber channels. Both was not simple and stupid as the best design should be. So IEEE 02.3M for the fast Ethernet and IEEE 203Z for gigabit Ethernet were the survivors. The original fast Ethernet cabling was 100 base T4, the twisted pair that runs for 100 meters, uses CAP3 UTP, and 100 base TX twisted pair that runs for 100 meters with full duplex 100 megabit per second. Last but not least, 100 base FX with fiber optics that runs to 2000 meters, full duplex with 100 megabit per second. The gigabit Ethernet can connect two stations or multiple stations through switches and hubs. Its cabling has 5 different cabling, 10 gigabit base SR fiber optics that runs to up to 300 meters with multi-mode fiber, and 10G base LR fiber optics also runs to 10 kilometers with single mode fiber optics. 10G base ER fiber optics that runs up to 40 kilometers with single mode fiber optics. 10G base SX4, these are 4 pairs of twin axial cable, and it runs for 15 meters. And last, 10G base T, that 4 pairs of unshielded twisted pair that runs for 100 meters, and it used category 6 unshielded twisted pair. Ethernet has been around for 20 years. It's simple, flexible, cheap, easy to maintain. People know it very well. And Ethernet works easily with TCP/IP, which is the most used protocol stack. There are 3 LAN standards, 802.3, 0.4, and 0.5, Ethernet, token bus, and token ring. They similarly have they roughly have the similar technology, and they both roughly get similar performance. But when comparing them, Ethernet is the most widely used, simple, easy installation, low delay at low load, but it's non-deterministic. There are no priorities, and the minimum frame is 64 bytes, and it has collision problems. The token bus, on the other hand, is more deterministic, short minimum frames, have priorities. It's good for real-time data. It has multiple channels, but it has a lot of analog engineering, including modems and wideband amplifiers. It's extremely complex protocol, substantial delay at low load, and poorly suited for fiber optics. And it has a small installed base of users. The token ring is easy engineering, fully digital, have priorities, excellent throughput and efficiency at high load. It has centralized monitor and delay at low load. So the winner is the Ethernet. As for wireless LANs, we will discuss the architecture, the physical layer, the medium access layer, frame structure, and services. There are 2 types of architectures. Infrastructure mode, that's in which the clients are linked to an access point, and access points are linked together. And ad hoc mode, where the clients are linked to each other without an access point. The architecture and the protocol stack for the IEEE 8.11. In the physical layer, we can see that it has evolved through the years. First was 802.11, the legacy with frequency hopping or infrared. Then came 802.11a with orthogonal frequency division multiplexing. After that, 0.11b with the spread spectrum. Then again back to OFDM, and last is MIMO OFDM. The first, the frequency hopping standard spread spectrum, and the infrared was up to 2.4 megabit per second. The OFDM was up to 11 megabit per second. The high rate direct spectrum spread spectrum was up to 54 megabit per second, and the OFDM again was up to 54 megabit per second. The multiple input, multiple output OFDM reached 600 megabit per second. With the wireless networks, we have problems that we cannot face with the wired networks, because with the wired networks, every station is able to sense the traffic that every other station sends. But with the wireless networks, the range of the radio frequencies might differ from one station to another, and that creates some problems. If you can see in figure A here, station A cannot sense station C, so it can falsely think that B is actually clear to send, and it starts sending, and this will cause a collision, and this is what's known as hidden station problem. In figure B, A can sense B, and when B is sending, A will falsely think that the medium is busy, so it will stop sending, and it will lose its chance to transmit. And this is what is known about with the exposed station problem. The supplier protocol here is SYSMA CA, SYSMA with collision avoidance, where when A is sending, B will sense the medium and find it busy. So it will wait until it's idle. When the medium is idle, it will perform as a random backoff and send the medium again. Now C's back off, C also want to send, and the C's back off was shorter than B's back off, so C will go first and send data, get its acknowledgement. B will wait until the medium is idle and reset its back off, then start sending again. So this way collision is avoided. This mode is called distributed coordination function for SYSMA CA. And there's another mode that has single point of coordination. It's called BCF, point of coordination function, where the base station broadcasts beacon frames periodically, and the base station can pull frames as well. And the third mode is DSC, DCF, and plus BCF at the same time. For DCF, we can see that the station can send requests to send and get clear to send. And the stations that are waiting can have both physical sensing to the medium and virtual sensing to the medium using what is known as network allocation vector. The network allocation vector will be set for the time needed for sending the frame and getting the acknowledgement, even if the acknowledgement was not sensed. So here, C will sense the request to send, and it sets its network allocation vector until the acknowledgement is expected. D sensed the clear to send, and it's also set its network allocation vector until the acknowledgement is expected. For more possibility for success in sending and receiving the frame without collision, the shorter the frame is, the higher the possibility of being transmitted without collision is. This can be done with shorter packets from the network layer, or to keep it transparent from the network layer with fragmenting dividing the frame into fragments. With each fragment has its own sequence number and its own checksum. The fragments are sent sequentially, and the protocol used here is stop and wait protocol, where each fragment has to have their acknowledgement before the next fragment is sent. The fragments are sent in pulses, and for the other stations, they sense the medium and they wait until the next acknowledgement is received before they try to send. For the other mode, the PCF, point coordination function, the base station broadcasts beacon frames periodically. The beacon frame contains system parameters such as hopping frequency, dwell times, clock synchronization, etc. The base station also invites new stations to sign up for polling service. Once a station has signed up, it will immediately have a certain fraction of the bandwidth, make it possible to give quality of service. And 802.11 pays attention to issues of power management, where stations can doze or go to sleep, telling the base station that it's going to sleep, and the base station can actually buffer the traffic that is send to this station and send it to it when it wakes up. For the combined mode DCF plus PCF, there are 4 intervals: short interframe spacing, where control frames and next fragments can be sent, and BCF interframe spacing, where frames can be sent, DCF interframe spacing, where also frames can be sent, and the longest extending interframe spacing, this is where bad frames can be retransmitted. 802.11 have 3 frames: data, control, and management. The frame generally consists of frame control, duration, addresses, data, and checksum. The frame control field have subfields. One of them is the type, which will say whether this was data frame, control frame, or management frame. 802.11 provides several services: intra-cell services, that is inside the cell services, that is authentication to authenticate a station, deauthentication to deauthenticate a station, privacy and data delivery. Inter-cell services, that you see between cells, which is association to associate a station with a certain access point, deassociation to deassociate the station from a certain access point, reassociation for the station to rejoin, and distribution and integration. See you in the next part.